So our last topic in our unit on stoichiometry is the concept of percent yield. So we have sort of three terms to introduce today. The first is theoretical yield, which you actually already know about, we just haven't attached the vocabulary word to it. So the theoretical yield is just the maximum amount of product that can be formed in a reaction based on the amount of limiting reactant available. So this is something, the theoretical yield is something that you already know how to calculate. You were doing these calculations in previous lessons when you were figuring out how much product can I form in this reaction. You were calculating the theoretical yield of the reaction. So that is the maximum amount that you can form if all of your limiting reactant is completely consumed and all of your product is perfectly collected. Now, in the real world, things aren't perfect. So we also have what we call the actual yield, which is the amount of product that you actually get from doing an experiment. So there are a number of reasons why the actual yield and the theoretical yield might be different. It could be that you as an experimenter made some mistake. Perhaps you didn't transfer your product completely to a different container. Perhaps you spilled somewhere along the line. Maybe you didn't completely mix your reactants. It might be that you didn't let the reaction run for long enough and it wasn't actually quite done yet. Or it could be that reaction just doesn't actually run to completion. Not all reactions do. In fact, many do not. That they just naturally stop before all of the limiting reactant is actually consumed. And in those cases, there's not always a lot you could have done about that. So it might be some lab technique that caused you to have a difference in your actual yield versus your theoretical, or it could just be an inherent part of that particular reaction. And the specifics of that is something that we get into a lot more in Chem 2. So the percent yield, which is our main topic for today, is just the ratio of those two things, is the ratio of the actual yield to the theoretical yield. So in terms of calculating, to calculate the percent yield, we're just doing the actual yield divided by the theoretical yield and then multiplying by 100 to put it into a percentage. So an example for today, we have this reaction between aluminum and oxygen to produce aluminum oxide. And we're asked what is the theoretical yield in grams of aluminum oxide when 5 grams of aluminum is allowed to react with excess oxygen. So this is very much like what you were doing last week. This is just a simple stoichiometric conversion, just with that new terminology piece of theoretical yield. But it's just asking you to calculate what is the maximum mass of aluminum oxide that we could get. So this is going to be the same as our stoichiometric calculations from last week. So we're starting with 5 grams of aluminum. We know that we always need to work in moles to do stoichiometric conversions. So we're first going to convert grams of aluminum into moles of aluminum, and we do that using the molar mass. So if we look at a periodic table, the molar mass of aluminum is 26.98 grams of aluminum is equivalent to 1 mole of aluminum. So again, this is our molar mass of aluminum is allowing us to convert between grams and moles. So at this point, we have canceled out our units of grams and we've made it into moles of aluminum, but we are ultimately interested in getting to amount of aluminum oxide. So we next need to convert from moles of aluminum to moles of aluminum oxide, and we do that using our coefficients. So if we look at our balanced reaction, it tells us that 4 moles of aluminum reacts to produce 2 moles of aluminum oxide. So that is going to be our conversion factor. 4 moles of aluminum goes on the bottom, since we need that unit to cancel. Our 2 moles of aluminum oxide goes on the top. So this cancels here. These are our coefficients. This is our coefficient ratio from our reaction. And then our last step is just going to be to convert from moles of aluminum oxide to grams of aluminum oxide. So we do that using the molar mass of aluminum oxide. If we add up from the periodic table the mass of 2 aluminum atoms plus 3 oxygen atoms, we get 101.96 grams of aluminum oxide is equivalent to 1 mole. So our moles here cancels moles here, leaving us in grams of our product, which is what we want. So this was our molar mass of Al2O3. So that gets us a total of 9.45 grams of product. So the maximum amount of aluminum oxide that we should be able to form from 5 grams of aluminum is 9.45 grams, and that is our theoretical yield. So in this case, we didn't need to determine the limiting reactant because we're essentially told it. We are told that the aluminum is reacting with excess oxygen. So if the oxygen is present in excess, then this 5 grams of aluminum is our limiting reactant, and we can go straight into that calculation without needing to determine which reactant is limiting mathematically like we were doing in our last lesson. So then the percent yield part comes in the next portion of this example. If a scientist isolates 8.54 grams of aluminum oxide product, what is their percent yield? So we've just found our theoretical yield up here. So this was our theoretical yield. This is our actual yield that we're given in this part of the problem. We're told that a scientist actually gets this much in the lab. So our percent yield is just the ratio of those two numbers. So our percent yield is just going to be the actual yield, which was 8.54 grams, divided by the theoretical yield, which we just calculated as 9.45, multiplied by 100 to get it to percent, and that comes out to 90.4%. So somewhere along that line, that scientist either lost about 10% of their material, or that reaction just tends to stop before it actually reaches 100% completion, and we can see that from the percent yield.